All right, so welcome to our 19th lecture on this beginner's course in algebraic topology. I'm N J Wildberger at the University of New South Wales. And today we're going to talk about an algebraic zip proof of the classification theorem of two-dimensional surfaces. So this is an alternative proof to the one that I sketched in the last lecture. And it's, the basic idea is due to John Conway, who is a very prolific and well-known mathematician at Princeton University, also the inventor of the game of life, and well-known for his work in group theory. And he, in the early 90s, I think he discovered another way of thinking about this classification that gives a new slant on things, and that I think will be interesting for us to look at. I'm going to present a rather algebraic look at Conway's zip proof. So what is the basic idea? Well, Conway likes to work with spheres, and spheres with additional structures put on them. What kind of additional structures? Well, for example, holes. So we could imagine having a hole. Or we could imagine having a cross cap. We can maybe picture like this. It's supposed to be a cross cap. That's like a projective plane glued to the sphere. That one's a hole. Or maybe a handle we get by taking two little discs and making tubes up from each of them and then gluing those tubes together. There's a handle. Or another version of that is something called a cross handle, where you take the two holes on the sphere, imagine having two tubes coming up, and we're going to join them up, but now not in the way we make a torus, but rather in the way we make a Klein bottle. Okay, so this one comes up. Maybe we'll have its flange there, and then maybe it comes in and joins with this one. That's supposed to look like a Klein bottle. All right. And so that's a different way of attaching two tubes coming up from the sphere, either as a handle or a cross handle. Now those pictures can also be replaced by something a little bit more algebraic. So another way of looking at those things is, say, a general hole. Well, it might have some sides. So we think of a general hole as maybe having edges labeled by A, maybe B, C, and so on. A cross cap can then be thought of as a hole with two edges like a projective plane. Like that. These are all now holes. So if we glue these two holes together, then we're going to get a cross cap like a projective plane. A handle, on the other hand, could be thought of as another hole with two edges, maybe E and E in this direction, and two edges F and F, just like a torus. And a cross handle could be thought of as something very similar, but maybe G, where these two sides, H and H, let's say, are in opposite directions. So this is the same kind of picture, but just in terms of holes whose sides have not been glued yet. So Conway's idea is, but instead of starting with lots of polygons, for example, let's have an example of a polygon. So this is the basic kind of object that we used in our traditional proof, a polygonal piece like this. And we had a word associated to it, say A, B, C inverse D. That was the word of the polygon. And there was also a little bit of ambiguity. We could rotate around, so this is by definition the same as B, C inverse dA. It doesn't matter where you start. Okay. So Conway says, let's think about this polygonal piece rather differently. Let's take this polygonal piece, imagine it's made out of cloth, and punch our fist through it, making a sac whose boundary is these four edges. And then we can think of that sac as actually being a sphere. So it's really the same, but we're just looking at that polygonal piece in a different way. We're now thinking of it as a sphere with a big hole in it. And the hole will be oriented just the same way that the polygon was. A, B, C, D. This is now a hole on a sphere instead of a polygon. So this is now a sphere with a polygonal hole. And we'll represent that by also a word, say A, B, C inverse D. But to denote the fact that we're thinking of it as a sphere with a hole, we'll put some brackets around it. And that'll alert us to that we're thinking about this a little bit differently from that over there. And of course, this is also the same as we can rotate the labeling, B, C inverse dA. Now something that we were allowed to do over here is flip the polygon around. We could lift it off the paper and put it down backwards, and that would have the effect of reversing all the letters, replacing the order and the inverse. So we could also write this one over here as A inverse, D inverse, C, B inverse, going in the opposite direction with inverses where there were ordinary ones before. And similarly here, that corresponds to taking the sphere and flipping it inside out through the hole. Right? We could just take the sphere, flip it inside out. The inside becomes the outside and vice versa. So we allow ourselves to write this as, say, A inverse, D inverse, C, B inverse. All right, so it's very close, but what's the advantage in thinking about it as a sphere with a polygonal hole? The advantage is we can consider more than one hole. So we can consider a sphere which has a bunch of holes. And so I'll draw one right there. Say A, B, C, D. That's a hole. And maybe a triangular hole. E, F in this direction, G. And let's make another hole with just one edge. Let's call it H. So now we have three holes, and we're going to represent a sphere with three holes in an extended way as we did over there. We'll write it just as a product of the individual holes. So this one here is A, B, C inverse D. That's that hole there. And this hole here would be E, F inverse, G inverse, and this hole just H. So we're going to record all the holes on a sphere. Red, each of them red with the same orientation. As a product, in fact, as a commutative product. Of individual holes or words. When I say the same orientation, we're on a sphere here, so I'm reading this one here. There's really an orientation like this on the surface of the sphere. I'm reading this one in that orientation, and we're going to read all of them in the same way to be consistent over the surface of the sphere. Now, well, we could, however, turn the sphere inside out. If we turn the sphere inside out, and perhaps it's simplest to think about doing that via another hole. But to turn the sphere inside out, we could turn it inside out through any one of the holes, but that makes it maybe a little bit asymmetrical. So let's just think about making another puncture, flipping the sphere inside out through that other puncture, and then closing that other puncture off after you're finished. Then what happens is that each of the individual holes has its word replaced by its inverse. So in this case here, we would get, say, D inverse C, B inverse, A inverse. It's easiest just if you read it backwards. G, F, E inverse, and H inverse. So that's a sphere with holes. But we want to have more than just one sphere. So we have a convention how to treat more than one sphere. For more than one sphere, what we do is we record the sum of the individual spheres. Okay, so for example, suppose we have two spheres, and A, B, A, C happens to be one hole there, and another hole, let's say, is a single one there with an edge A. No, sorry. Or edge D. And over here we have a single triangular hole. Let's say D, B, C. All right, so we could regard the union of these two things as a combinatorial surface, call it M, and we'll represent it by a sum of the individual combinations of the holes. So this one here would be the hole A, B, A inverse C, together with the hole D. And this one would be B, C, D inverse.
There were no edges that were on two different holes.
No, yeah, the question is, there were, in this example, there were no edges which are on two different holes. That was just not necessary. The edges can be common to different holes or to different spheres. They can be distributed as they like. In fact, now we can sort of think of a combinatorial surface as an expression like this, if we want to. So we might even be able to make a definition that a combinatorial surface is an expression consisting of a sum of products of words, each in letters A, B, C, and so on, and in their inverses, with each letter appearing exactly twice. With some equivalences or notions of equality. Which I have yet to explain. All right, so Conway's proof was very geometric and in fact doesn't require an algebraic framework like this. Okay? Conway's proof roughly is that we start with a polygonal surface as a bunch of polygons with edges, exactly two appearing, and we think of each polygon as a sphere with a hole in it. Okay? And what we're going to do then is we're going to take all these spheres with holes and we're going to zip the edges together. That's why it's called the zip proof. So we take an edge A that may occur in one hole somewhere, and we look for the other occurrence of A, which is somewhere else, might be on the same sphere, might be on the same hole, might be on a different hole, might be on a different sphere altogether. And we're going to take that edge A and that edge A, and we're going to zip them together. And look to see what happens as we build up the surface by zipping together all the edges. We're going to do this until there are no more free edges, no more holes, and just a surface. And basically his argument is that if you start with, basically we are starting with spheres with holes. We're starting with a sphere with holes, with cross caps, handles, and cross handles. And okay, in this, as we're starting, there happen to be no cross caps yet, and no handles yet, and no cross handles yet. But as we glue or zip these edges together, it's not too hard to see that at each stage, having handles, cross caps, and cross handles is preserved. That property is preserved under any of the various possible zippings together. So you have to examine the various possible zippings. What happens when you zip two that are on the same hole, two in different holes, or two on different spheres. All right, I'd like to present that a little bit more algebraically because I think it's kind of interesting to have a very computational approach to the subject that could conceivably be implemented by a computer. So someone could write a program to manipulate these expressions and create surfaces or classify surfaces from rather random expressions. So we have to explain what these various notions of equality are. Okay, so the notions of equality that we're allowed to use to go from one expression to another. Well, we've already mentioned some basic ones, the ones that involve rotating a word and the ones that involve inverting a given sphere. Okay. But in addition, there are some other ones that we would want. And the first one we'll call zipping spheres. Okay, so we have two spheres, and on one of them we have a hole with an A edge, and the rest of it I'll denote by X. So X, the letters in the alphabet like X, Y, Z will typically denote variable edges, combinations of edges, and the actual edges themselves will typically be A, B's, and C's. All right, so there's one hole, and there might be some other holes on this sphere. Let's put it in a U representing some other holes. And over here we have another sphere, which also has an A edge, but the A edge is going in the opposite direction as we're looking at it in this orientation. So A, Y, and then there might be some other stuff, Z. Okay, maybe I'll put a second hole here. So maybe U and W. Okay, so how would we represent this hole? Well, there's a word for the hole U, there's a word for the hole W, whatever they are, and then this hole is, say, XA. And over here, this one has A inverse Y, and also another hole Z. Now what we should do is we should think about this as, let me just put these things on the side, and let me make make them like tubes with the holes almost together. So there's our sphere, first one, and it still has its U hole and its W hole somewhere. But over here is the hole that we're interested in, and it's the hole with an A here and an X here. So that's sort of looking inside the sphere. And now we'll take this one here and we'll move it over here. So blob like this. It's got some hole Z on it. And over here, the A is in this direction, and the Y is in this direction. And that's sort of looking inside it. So I've got them lined up. We're going to zip together the two A's. So what happens when we zip together the two A edges? So there's, to zip together these two A edges. Well, we're going to get kind of a blob shape. There's still going to be our Z hole over here, our U hole here, our W hole here. And the old A edge, so sort of the back here. And now this X and this Y piece, let's do it like this, are going to form a new hole. So the old A pieces are back here. And so now we can write this as a single sphere, U, W, X, and Y together, and Z. And if we ignore these extra words, the essential aspect is that if we have one sphere with a hole XA and another sphere with a hole A inverse Y, then we can combine them to get one single sphere with a hole XY. So we've zipped together two edges, and the two spheres have become one sphere. So that's our first allowable, first new operation. And our second one is well, we could say zipping same direction edges in a hole. So a sphere. We'll have a hole with a side B and side not same direction, opposite edges, opposite direction rather. This is zipping opposite direction edges in a hole. So we have B, B, and maybe some sequence of words X, some sequence of edges Y. And there might be some other holes too. Let's represent them by U. Okay, so we're looking at a particular hole that has an edge B and another edge B in the opposite direction, and we're going to zip those together. And when we do, we get a single hole X on one side, and kind of a dotted line where the edge B used to be, and then another hole Y on the other side. There's still our sphere, and the other holes on the sphere have not changed. So we can write this as X, B, Y, B inverse. That particular hole can be replaced by hole X, hole Y. And if there's a hole U in front, then it stays there as well. But the crucial relation is that X, Y equals X, B, Y, B inverse. And it's important to recognize that we can go both ways. Not just zipping a hole, but if necessary, we can have two holes, and we can combine these two holes into a single hole by creating a new edge B. So it's not just a way of zipping together holes, it's also a way of, not just a way of zipping together edges, it's also a way of coalescing two individual holes to get a bigger hole. To go from here to here. And the third thing that we need is separating cross caps and handles. Okay, so these are rather special things. Suppose we have a hole that has an A edge and another A edge right beside it, and then an X. That's a hole. Then if we look at the neighborhood of this vertex here, if we go in this direction here on the surface of the sphere, then we're moving to the bottom of the A edge. The bottom of the A edge here moves to the top of the A edge there, and the top of the A edge here moves to the bottom of the X edge. So what ends up happening is that this vertex here, let's call it capital A, is associated with this vertex here, also with this vertex here. And the fact that these two vertices are actually the same after we glue means that we can think of the A and the A piece together, and then there's the other hole forming the X hole is adjacent, and there's nothing preventing me, because I can move holes, I can move that extra hole away. I'll put it separate. So this is the hole X. So in other words, I've gone from, and there may be some other holes U, let's say. So from some U, and then from a word AX, where X is some arbitrary sequence of letters, I go to U, A, and then X. So I can separate that cross cap from the rest of the letters in the hole that it appears, if the A and the A are adjacent like this. And then there's the same argument, same for what happens when you have a handle. If you have a word like U, A, B, A inverse, B inverse, times, say, some Y, exactly the same argument shows that you can separate that handle from the rest, A, B, A inverse, B inverse, creating two individual holes. One is now a pure handle, just as we now had a pure cross cap or projective plane before. Okay, so now our strategy for the proof. What we want to do is we want to start with an arbitrary combinatorial surface. Start with combinatorial surface, which is connected. And that means that when we zip together different spheres or different polygons, after zipping, we get one sphere. So we start off with the same way we started our proof with our traditional proof, with lots of polygons. We reinterpret the polygons as spheres with holes, and then we start zipping together different spheres along common edges to get just one connected surface. Okay. So you can have a sphere with some big hole. Lots of different labeled edges. Okay, and then after that, we are going to zip together opposite direction edges. According to our second operation, to get still one sphere, now with many holes. The number of edges is going down, but the number of holes is increasing. Okay, now what do we do? Zip together same direction edges in a hole. Okay, so let me explain that important step. And it's reminiscent of what we did in the classification theorem, but it's somehow stated a little bit differently. So suppose we have a hole that looks like this. So there's an edge A, and then some sequence Y, and then another edge A in the same direction, and then some more stuff X. And there might be other holes too, say V and U. All right, so we have V and U, and then we have this hole A, Y, A, X. Okay, so what we're going to do is we're going to manipulate this. VU AYB plus B inverse AX. So I remind you there was a rule that was like this: XA plus A inverse Y equals XY. Remember that one? That was one of our basic rules. So we're using this and thinking of this thing here as being a combination of two things, and separating it in two words by introducing a new edge, in this case B. So the AY and the AX are separated with a B and a B inverse. Right, okay, so then we're going to rearrange this as V, U. We'll just rotate this around, Y, B, A. And we'll rotate, this is a new sphere. So we're allowed to invert this sphere. Inverting that sphere means changing the orientation and replacing all of the things with inverses. So that would be like A inverse, and then B, and then X inverse. And now I perform the same thing that I did over here, but in reverse. Now I think of A and A inverse as being the common interior edge, and I'm going to contract there, giving V, U, and then Y, B, B, X inverse. And then I can write this as V, U, B, B, X inverse Y. And now that's a cross cap that's separate. We can separate that from the rest of the word. So we can write it as V, U, X inverse Y. So they're still on the same sphere exactly. The cross cap is just another word on the sphere. That's the rule. All right, so where have we got? We've gotten cross caps kind of dealt with. Now how to get the handles. Okay, so I think the next step that we're going to do is looking at zip together holes on a sphere. So suppose we have, say, U, X, A inverse Y. So we have two separate holes with an A and an A inverse appearing in those two different holes. Then what we can do is we can write this as U times X, A, B, A inverse Y, B inverse. That was another way of combining two holes by essentially creating an edge in between them, the new edge B. And now the idea is to manipulate this so that we get a handle out of it. And it's a little bit reminiscent of what we did in the traditional proof, but we'll just do it here in this context. So we'll get U times, let's write it as B inverse X A B. Okay, A B. A inverse Y first. And then U, B inverse X, A, B, and I'll separate right here, putting in a C plus a C inverse. And this is then U, rotating around, B, C, B inverse X, A, plus A inverse Y, C inverse. So I've rotated now so that the A and the A inverse are side by side. And then I will use them to combine. U, B, C, B inverse, X, Y, C inverse. And that gives us U, maybe C inverse, B, C, B inverse, X, Y. So it's a manipulation that it's extracted a handle that we can now separate from the rest, equals U, C inverse, B, C, B inverse times X, Y. So basically, this gives us enough technology. We can zip together same direction edges. We can zip together opposite direction edges. And so continuing, we get a sphere with cross caps and handles. So I haven't talked about cross handles. Cross handles are really just two cross caps. And this is sort of in parallel to the proof that we did last time. And then we have to argue, as we did before, that cross cap plus handle is the same as three cross caps to get it in the standard form, if we want to. But I think it provides an interesting sort of algebraic framework that conceivably somebody could write a program, and maybe an interesting exercise for aspiring programmers, to write a little program that takes an arbitrary expression, which is a combinatorial surface, and goes through and creates a bunch of cross caps and handles at the result. All right, so it's a very beautiful theorem, this classification of two-dimensional surfaces, and it has lots of consequences. Next time I'm going to talk about the connection between these different kinds of surfaces and classical geometries. Right? So it turns out that the Euler characteristic sort of separates all the two-dimensional surfaces into three classes, and corresponding to spherical geometries, Euclidean geometries, and hyperbolic geometries. And the connection with the surfaces and the geometries is quite an interesting and important one. So we'll see you then.